Hey guys, welcome back to Calculus. Today we're going to be talking about the differentiation of the trig functions. So you saw this image in your last video, and so just going through to see what we've done so far, we have taken derivatives using the definition of derivative, but we figured out that that is going to be a really long process to follow for all of the different types of functions that we've used. So right now we're learning different derivative rules or shortcuts to find derivatives of all the different types of functions. So we have found a derivative rule for functions that look like polynomials. We've used derivative rules for functions that were being multiplied and also functions that were being divided. So we did power rule for here, then we did the product rule, and then we also did the quotient rule. Well, now it's time to look at what's the rule for finding the derivative of a trig function. So these are on page 48 in your notes packet. We could find the derivative of a trig function by doing sine of x plus h minus sine of x over h, but once you get here, it's like, ooh, what do I do? How do I evaluate that limit? So let's look at a better way. So here's a graph of sine. We're going to try to estimate this derivative using tangent lines. So here is sine, the original function, and we want to know what is the derivative of sine. So we're going to approximate the slopes of tangent lines of sine x at specific spots. And so it's easiest to start about right here. So I look right here and I say, oh, look, at x equals pi over 2, the tangent line would be horizontal. So the slope of the tangent line, which is we also know as the derivative, so the slope of the tangent line to f of x at x equals 0 would be 0. Then I also see like a minimum would also be another place where f of x would have a horizontal tangent line. So at 3 pi over 2, I'm going to estimate the derivative to be 0. Then I'm going to start to look right here. So I look at the slope at, I put that in the wrong place, didn't I? When x is pi over 2. When x is pi over 2, slope is 0. Okay, now when x is 1, it looks like the slope, looks like I'm going up 1 over 1, up 1 over 1, up 1 over 1. So it looks like the slope would be about 1. And then also right here, it looks like the slope would be the opposite of that, negative 1. So that would be at pi. And then at pi over 4, it's a little, let's see, it's going up and then it's going to kind of level off. So it's a little less than 1, but it's still positive. Not less than 1. Well, it is less than 1, but it's still positive. So positive and less than 1. And then at 3 pi over 4, it looks like it's negative, but not quite negative 1. Then at 5 pi over 4, still looks kind of negative, but it's kind of flattening out, so still negative. And then at 7 pi over 4, the slope would be about, I don't know, a little bit less than, maybe 1/2. And then at 2 pi, the slope looks like it's 1. So let's plot these values. So 0, 1. When x is pi over 4, that was hard to determine, but when x is pi over 2, we had a point at 0. So less than 1, let's say maybe somewhere around here-ish. Maybe we can see a pattern. And then at pi, the derivative we estimate to be about negative 1. Then at 3 pi over 2, we estimate the derivative to be 0. And at 2 pi, we estimate the derivative to be 1. So if I connect these dots, I'm getting another wave. Does anybody recognize that graph? The graph that starts high and goes low, and it's not quite sine. Oh, that looks like cosine. So the derivative of sine is cosine. Okay, we will remember that. And for reference, here's a picture of cosine. Okay, so if the derivative of cosine is, or derivative of sine is cosine, let's estimate what the derivative of cosine would be. So when x is 0, looks like the derivative would be 0. So I'm going to put a point at 0, 0. And then at x equals pi, the derivative would be 0. And that also happens somewhere where x equals 2 pi. Derivative is 0. So I'm going to plot points here and here. Then it looks like at about pi over 2, it looks like we have that -1 slope. So pi over 2, -1. And then 3 pi over 2, looks like we have a +1 slope. So at 3 pi over 2, +1. So if I connect these points, oh, it's another wave. Looks like, now sine, it looks like sine, but it's backwards, or the opposite. So this is actually negative sine. All right, so here's something you need to memorize. The derivatives of the two definitions that we're going to use all the time. The derivative of sine is cosine, and the derivative of cosine is negative sine. You need to have these things memorized. And I know we're in virtual learning right now, but even though we're in virtual learning, these derivatives are going to come up so much that if you don't have them memorized, it's going to be really, really annoying. So those are the derivatives of the two trig functions, but there's actually 6. We need to know what's the derivative of tangent, what's the derivative of cotangent, what's the derivative of secant, and what's the derivative of cosecant. So we need to know derivatives of all 6 trig functions. Now we can find those with the different rules we've learned already. Now I have y equals sine of x right here. Right now, I do not have a rule that will tell me the derivative of tangent. But I do know from pre-calculus that tangent can be rewritten as the sine of x over the cosine of x. That is a trig identity because tangent is the same as sine over cosine. Now I have a quotient. And I can find the derivative of my quotient with the quotient rule. So let's try that, dy dx. The quotient is low d high minus high d low over low low. So I'll start low cosine. Derivative of the high, so derivative of sine is cosine. So low d high minus high, which is sine. Derivative of the low, what's the derivative of cosine? That's negative sine. All over the low low squared, or all over cosine squared. Now, if I combine this, cosine times cosine is cosine squared. Negative sine times negative sine is positive sine squared. All over cosine squared. Now, what is cosine squared plus sine squared? Well, there was a trig identity for that in pre-cal. Sine squared plus cosine squared is equal to 1. So dy dx is the same as 1 over cosine squared of x. And 1 over cosine squared, we don't know what 1 over cosine squared is, but we can write it as 1 over cosine times 1 over cosine. And 1 over cosine is the same as secant. And 1 over cosine is the same as secant. And secant x times the secant x is secant squared of x. So the derivative of tangent oops. So if y equals tangent, then dy dx equals secant squared. So now we have the derivative of sine, cosine, and tangent. So that's another thing you need to have memorized. Now cosecant, I can find the derivative in a similar way. I don't have a definition for cosecant, the derivative of cosecant, so I'm going to try to rewrite it. Cosecant is the same as 1 over the sine of x. So now I'm going to try to find the derivative using the, I need to change my color here. Find the derivative using the quotient rule. So dy dx is low sine, derivative of high, derivative of 1 is 0, minus high, which is 1, derivative of low, derivative of sine is cosine, all over low, so all over sine squared. Okay, so sine times 0 is sine. So the numerator looks like it's going to be negative cosine of x divided by the sine squared. Now I don't know what that is, so I'm going to rewrite it. Negative cosine of x over the sine of x times 1 over sine, because that would still give me sine squared in the denominator. Now negative cosine over sine is negative cotangent of x, and 1 over sine is cosecant of x. So this is the derivative of cosecant. So if the function is cosecant, the derivative of cosecant is negative cotangent cosecant, but you will see it written in most books as negative cosecant of x, cotangent of x. Now, do you want to do what I just did? You just saw me do two proofs. I proved that the derivative of tangent is secant squared, and then I proved that the derivative of cosecant is negative cosecant cotangent. Do you want to do that proof every time? No, nobody does. And in fact, I don't even want to do the proofs for secant and cotangent, mainly because they work out the same way. So here is the proofs for those two. What you need to do is you need to memorize your 6 derivatives. So take a picture, write this down, but you need to know your 6 trig derivatives. Get out all the colors, highlight, Post-its, whatever you need to do. But you need to memorize these. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of secant, derivative of tangent is secant squared. Derivative of cosecant is negative cosecant cotangent. Derivative of secant is secant tangent. And then the derivative of cotangent is negative cosecant squared. Now, one thing I always like to point out to my students, the derivative of the cosine, cosecant, cotangent, all those derivatives are negative. The other ones are positive. So that might help when you're looking for patterns to memorize. But memorize those. And the next thing you're going to do is an exercise in memory. These derivatives are going to pop up so much that you're going to need to have them memorized very well.